Okay, so let's take a look at abstract base classes and then we'll move on to some other examples. Abstract base classes or abstract superclasses are also in Java, and the idea is basically the same in C++. If you have pure virtual functions, those are in Java we refer to this as abstract methods, that is methods with no method bodies. Same thing as pure virtual functions in C++. They require no definition. We don't say what the method or the member function body is. And if you use that in a class, therefore that class is by default, in the case of Java, it would be an abstract class. If you have a class with at least one abstract member method, it becomes an abstract class in Java. Same way in C++. A class with just one abstract or pure virtual member function makes the whole class an abstract class. Differences in Java, you have to have the abstract keyword. Okay, so the thing is, this forces all derived classes to define their own version of these member functions, which are pure virtual functions in the base class. A class with one or more pure virtual functions is an abstract base class. This can only be used as a base class. You cannot instantiate it. So if you have an abstract base class, just like in Java, you could not instantiate an abstract class. Same rule, basically, in C++. And this is also, if you remember interfaces, remember all interfaces will have only abstract member methods. And so if you implement an interface, you have to set up your own function body or method body for the inherited or implemented member methods. Same thing, same basic rule here. If you have a class with pure virtual functions, it's abstract, it can be used as a base class, so it cannot be instantiated. And so if you have a derived class that extends this abstract base class, then it has to define all of the abstract member functions, and if it fails to define any one of those pure virtual functions, then this derived class also becomes an abstract class. The same thing in Java. Okay, so the whole idea of using virtual is so that you can use polymorphism. Okay, so for example, in the previous set of examples, we looked at the discount sale. That every discount sale, since discount sale inherits from the sale class, every discount sale object we say is a sale object. But the reverse is not true. Every sale object is not necessarily a discount sale object. It can be just like a regular sale object, and some of them can be discount sale. Okay, so it only goes one way. In this case, every discount sale object is a sale object, but the reverse is not true. Let's take a similar example. This is from the book. Hope you can see the text. We have a pet class, and this is not something we want to do very often, but just for this simple example, we make our data member name, which is a string, we make it public. And then we set up a print method that prints out just the name. Okay, and then we set up a dog class which extends or inherits from the pet class using public inheritance, and it adds, in addition to the name string, it also has a breed string, and it has its own print member function. So if you let's quick scroll down and take a look at what these things do. In the case of pet, all it can print out is name because it doesn't have a breed data member. In the case of dog, it can print out the name and the breed. That's the only difference. So these are all things you usually do not want to do in classes. You do not want to use cout. You do not want to use public data members. But this is just an illustration. This is straight from the book. I normally wouldn't even put it, except this is a good example. Alright, so the idea is, once again, dog inherits from pet. So we can say all dogs are pets, right? But not all pet objects are necessarily dog objects. So we can say a dog is a pet, but we cannot say that a pet is a dog. Sometimes a pet object might actually refer to a dog object, but in general, we cannot say a pet is a dog because not all pets are dogs. Okay, so once again, a dog is a pet. So that relationship goes one way. So definitely ask if this is not making sense. This is a relationship is super important for really understanding how polymorphism works. Remember, it goes one way, not the other way. Okay, so here's this example that we just looked at. And now let's say we are given declarations, a dog object. It's an instance of dog. Remember, you're calling the default constructor when you do this, right? So you're actually creating a dog object, an instance of the dog class, and here we're creating an instance of the pet class. So remember, we shouldn't do it, but we made the member data members name and breed. Those two data members are public. And this is just for example purposes. Typically, we do not make those data members, any kind of data members, public if we can avoid it. Okay, so here is where you want to pay very close attention to what we're doing, because this is no doubt it's going to show up in your programs. It's going to be important in quizzes and things like that. Anything that is a dog is a pet. Okay, but not every pet is a dog. So you can make assignments of this kind. So let's say you have, let's just go back quickly. We have vdog instance of dog, vpet instance of pet. You can say vdog.name is equal to tiny. We're assigning a string to this public data member name. We're assigning another string to this public data member breed. We're assigning it Great Dane. This we can do. Vpet is equal to vdog. And this works only because of inheritance. Dog inherits from pet. You cannot say vdog is equal to vpet. Even after you make vpet actually refer to the vdog or anything like that, you cannot assign it the other way from this. This is okay, but we cannot say vdog is equal to vpet because not every pet is compatible with the dog. Okay, I hope that makes sense. It is really, really important. If you have to pause and like think about it or check it out or ask questions, definitely you want to do it now. Okay. So we can assign values to parent types, but not the reverse. So pet is a parent of dog, so you can assign dog to pet, but not the other way around. Okay, when you do this, you get what's called the slicing problem in C++, which does not happen in Java because C++ just works differently. Okay, notice the value assigned to vpet loses its breed field. So if you try to do this, cout vpet.breed, even though vpet is pointing to this vdog, which has, actually, let me take that back. Even though vpet was assigned the value of vdog, which should have a name and breed, when you do this, it turns out there is no breed data member. Even though we assigned a dog to vpet, there is no breed. vdog had a breed, but vpet does not have a breed. So let me just scroll back up. vdog has a breed, sorry, dog has a breed data member, pet does not. When you do this, this will give you an error message. That's because it's sliced off. The dog object was sliced off. The breed data member and all the extra data members that came with dog objects were sliced off when you did this. So this is the crucial statement. This will show up many times, and you just want to be clear about what this does. When you do something like this, you slice off the dog parts that are not in pets. Those are all gone, and now you're left with a vpet object with only a name and no breed. Okay, so the slicing problem is super important, and you can follow this link. There's a Wikipedia article on object slicing. Very important to read this. This might seem appropriate in some instances. The dog was sort of moved to a pet variable, so it should be treated like a pet and therefore it should not have the dog properties. Makes for all kinds of interesting philosophical debates. We're not going to look into that. In C++, this slicing problem is a nuisance. So this object that we assign, this dog object, is a Great Dane named Tiny. We'd like to refer to its breed even if it's been treated as a pet. And in Java, we actually used to doing that a lot. We do that a lot. We set up an array of, let's say, pet objects, and in there we can have actual pet objects and dog objects, and we can treat the pets as pets and dogs as dogs. That's what we want to be able to do. And it turns out we can do so if in C++ if we use pointers to dynamic variables. So that turns out to be the key. So instead of using the stack and variables that are allocated on the stack, we can use pointers and have them point to dynamic variables. That's variables that point to memory on the heap, and then it turns out we can get things to work.